Today we're going to talk about wells, or well models. There's really two types of wells we deal with. Constant rate wells. And if we have a constant flow rate, then what we want to know is what the pressure versus time is at the well. Right? If we set the rate, then the pressure is a consequence. Or alternatively, we can have a constant bottom hole pressure well. And in that, we want to know what the flow rate is versus time. So if we set the bottom hole pressure, then we compute the flow rate. By the way, there is a sort of a strange occurrence that can happen in a reservoir simulator with a bottom hole pressure well, and that is if you have multiple wells in the reservoir, and say some of them are constant rate, some of them are constant bottom hole pressure, it's not always easy to know what the flow rate at one of the bottom hole pressure is going to be as you deplete the reservoir. And you could actually, what would happen if you were to deplete the reservoir below the pressure at which the bottom hole pressure well is set at? Your producer would turn into an injector, right? And so that can actually happen in your reservoir simulator, and if it does, you know what would happen, right? Of course, if this happened in real life, you'd shut in the well or something, right? But it can certainly happen in your reservoir simulation. So if you see your injectors become, your producers become injectors, that gives you an idea of what's happening, or what happened. So we're going to work on some derivations today, but what we're after, and I'll give you a sort of a clue as to what we're after. We're after some model that could tell us what the flow rate is of a well as a function of some productivity index at, say, the L grid block times the pressure in the L grid block minus the pressure in the well. So the way we're going to come up with this, we're going to start with the radial diffusivity equation. So I think on your second homework you derived this. First or second homework? Or not necessarily derived it, but you worked with it and finding differences. And so it's something like phi mu Ct over K PdT 1 over R. So this is the radial diffusivity equation. And in the derivations that are going to follow, we're going to work with the analytic solution of this. Okay? And I guess to give you some context of what we're after, why we're trying to do this, of course, normally in a normal grid block, and the grid blocks can be vast, right? I mean, in a real reservoir, our grid blocks might be on the size of tens to hundreds of meters, right? And then you have an 8-inch wellbore in the center of it, set at some pressure that can be very different than the reservoir pressure. And so you can have a very steep change or a very sharp change from where your well is to whatever your average grid block pressure is, right? So it can be very different. And if you don't do something to sort of correct for that or account for it, it can give you very bad results or not physical results, right? Because you have a very small area of vastly different pressure from your reservoir, and there's a steep gradient that goes away from it. And so we're trying to do something in our simulator to correct for that, as opposed to just assuming that the entire vast grid block is set at the, because I mean, what else would you do, right? The other thing you can do is if you have a grid block that's on the order of kilometers and you have a well in the center of it, bottom hole pressure well, you'd have to set the whole grid block at that pressure. Right? Well, that's not a very good approximation either. So we're going to work with the analytic solution of this equation, or specifically we're going to work with the analytic solution to the steady state version of this equation. So we're going to assume that the time dependence is 0 so that we have a steady state. And now we have an ordinary differential equation that we can solve when we have some boundary conditions. So the two boundary conditions that we're going to work with, boundary condition number 1 is basically going to say that when the limit as r goes to 0, the flux is equal to Darcy's law. So this is like the divergence of the flux. So we're going to say that in the limit of r, as r goes to 0, so the divergence at a point is equal to Darcy's law. So that's boundary condition number 1. And the other boundary condition is that we're going to say that the pressure is equal to some reference pressure at a radius equal to some reference radius. And we'll talk about what those reference pressure, reference radius are. But in terms of solving this, we can just solve it in terms of those, right? And it won't matter. So who knows how to solve this differential equation? I mean, who's it like? What's the technique you would use? Right? You all took a class in differential equations, right? So maybe you'd use something like method of undetermined coefficients or something like that. Yeah. Actually, no, I wouldn't. You could. I think this guy is separable, though. I think if you use the product rule of this derivative, you could separate, and then you could separate the dp and dr, and you could integrate it. Right? So this would be like separation of variables. But you know what? I wouldn't do that either. Let me show you how I solve a differential equation. Because I'm an engineer. I'm not trying to impress you with my math skills. I took differential equations a long time ago. I took partial differential equations a long time ago. I passed those classes. Now I just use differential equations to solve engineering problems, right? And so I use the tools available to me. I use the tools in front of me. Right? I use a computer. So who's ever solved a differential equation in MATLAB? Can MATLAB solve this guy analytically in closed form? I think it can, actually. If you use a symbolic package within MATLAB, I think it can. But it's too much syntax, and I don't like it. So I prefer to use Mathematica for something like this. So has anyone ever used Mathematica? So I'll show you a little bit of Mathematica. And, I mean, I'm not trying to show you this to make you learn a new tool or anything. I'm just trying to show you this to expose you to new tools. And you know, I hear a lot of complaints from students. Well, we were taught MATLAB. I don't know Python. I don't know Mathematica. Well, I mean, you know, really, you want to be proficient in lots of tools so that you can solve the problem as quickly as possible with, you know, choose the best tool for the job, right? Choose the best hammer for the nail. And in my opinion, in this case, of solving analytically, symbolically solving a differential equation, I don't think there's a better hammer than Mathematica. So I'll just briefly do this for you just so you can see it. So what I'm going to do, one of the nice things about Mathematica is I can just type the equation in pretty much like it looks on the paper. So I'm going to say the equation is 0 equals to 1 over r d r p r. So the syntax there is the d is take the derivative with respect to r, so the comma r. Take the derivative with respect to r of r times partial p r. So the tick mark is like saying the first derivative with respect to the argument. So then if I execute this guy, it just does the product rule or computes that derivative, right? Computes the derivative. So that's the derivative, okay? And then this is the equation I'm going to solve. So it's as simple as d solve equation PRR. And that's the solution. That's the general solution. Of course, there's some constants of integration in there that come from the boundary conditions. And it's possible to actually include the boundary conditions in desolve, and it'll spit those out correctly. But in this case, it's easy enough to just sort of do it by hand, and it gives me an opportunity to show you how you can use mathematically to solve a linear system of equations too. So what we're going to do is just evaluate. So I'm going to have equation 1 is PR evaluated from sol. So let me just show you what that looks like. It just returns PR from the solution up there. And one of the boundary conditions was we said that we want this when R is equal to some R ref for this whole thing to equal P ref, right? So why did not oh, there we go. So it just plugged in R, it plugged in RF for R in that equation and set it equal to P ref, right? So that's one equation. The second equation was we said that the flux, which is like R d P R slash dot sol R. I don't know if I need these parentheses or not, but that is equal to Darcy's law. So we said minus QW mu BW two pi KH. Okay, so then I can just solve these guys. So so now we solve a linear system of equations. Solve equation 1, equation 2 for C1 and C2. Right. The first just gets rid of that extra set of parentheses. Right? So then finally I can say that PR slash dot sol slash dot sol2 is my solution. So that's the solution to the ODE. It's kind of funny looking. Let me. Okay, so I don't really know why it doesn't simplify it more. You could probably make it. Probably because it makes no assumptions on whether these are real numbers or something. I don't know, but basically you can see that if I separate the numerator into this over that plus this over that, then this cancels and I just have P ref there, right? And then I can factor out a negative sign, so I have P ref minus log of R minus log RF. And everybody remember the rule of logarithms. If they're subtracted, then you can put them in the division inside the logarithm. Right? And so that's how I'm going to write the final solution to the equation. I'm going to write it like this. PR is equal to P ref minus QW mu so that's straight